Okay. Do people just want to get started since we're here?
Sure.
Okay, go. Yes.
So in one of your videos, you were doing a problem, an electrochem problem, and you threw out a battery. I have it drawn here. It's for mercury, and you didn't have an electrode because we used liquid mercury, and I was wondering why we can't just use platinum for the electrode here.
Yeah, that's kind of like the one I did in class. I don't know if it was way back, pretty long time ago.
Yeah.
Well, because we already have a metal, so we don't need another electrode.
Okay.
The metal itself acts as an electrode. It just happens to be a liquid instead of a solid.
Yeah. Okay. And we don't.
So it'd be like if you had an electrode in the solution and you added another one.
No, that's good.
Yeah.
No, there's no need for
Okay.
that.
And we don't use this.
I don't know. I like the old one.
No.
Yeah, you don't use ionics.
Okay.
They're not necessarily good. They're not metals. They're not necessarily good conductors. Just like salt, table salt, they don't use it to conduct electricity. Yeah. Is that all right?
Yeah. Thank
Okay.
you.
Cool. Who's next? That was easy.
Okay.
Yeah. Oh, this is being recorded. I don't know if it's going to be posted, but it's there if I need it.
So for this one.
If I can edit it. Yeah.
It says any monobromo, whatever.
Bromination products are possible.
And I
Yeah.
thought there was 6 because I do it little design. I know this
Okay.
is more
That was less than 6. Let's see.
It's 5, but I thought it was 6.
2, 3, 4, 5. I agree with 5.
Why is it 5?
Okay. Is this from the discussion worksheet? Or is that from?
Yeah.
Okay. From the discussion worksheet, or something that looks like this. And then there's monobromination. So that means where you halogenation is one of our reactions. Well, this is the most common place to put it. That's 1. Okay. That's 2. Okay. 3 would be different than the other 2, so we're at 3 now. 4. Okay. And 5.
Oh,
If you put it here, it's the same as putting it here. Put it here, it's the same as putting it there. Is that alright?
yeah.
Okay. Cool. Who's next? Yeah.
I have a question for the discussion worksheet.
Okay.
Some of the degrees of unsaturation.
Okay. C3H6O. Just to calculate the degree of unsaturation, that's it? Or
No,
to
it's
solve
actually
the problem?
Yeah, it's doing the whole thing where we draw the structural isomers.
Okay. Sure. So the degrees of unsaturation, it should be Cn, or C3, H2n plus 2, or 8. Is that okay? 2 times n plus 2, 8. So it's missing 2. So it's 1 degree of unsaturation. Is that part okay?
Yeah.
So that means there's either a ring or a double bond.
Oh, and we don't take into account the oxygen?
Nope.
Oh, okay.
Yeah, never take into account the oxygen. You're going to take into account halogens. Oh, we don't have a halogen here.
Okay.
Okay. So then you just have to start doing stuff. So I'll start with the double bond, meaning the chain. So this would be the only possible chain. Now I have to put an oxygen on it. I guess it could vary a little bit. Let's see. Oh, this is one possible chain. So I can put the O there, but I can't have an O by itself. It would violate formal charge of 0 rules. So I could have the O here, or here. Is that okay? As a warm-up? Okay. Then the double bond could also be on the O. So I could have a couple options of that, like this, or that. All right? And I could have an ester, or not ester, ether, like that. And I need a double bond though. Okay, I can't think of any more chains. If somebody has another one, I'm having drawn on there. On the test, I would probably, if I was doing this on the test, I would like write down all the ones that I could think of, and then probably come back to it at the end, see if I think of any more. Be helpful, just get a second look at it. But this is all I think of. Then we have to go to rings in just a second. Yeah.
On the bottom right one, why can't it, bottom right?
Yeah.
Why can't it go like one more to the right? The bond.
You want the O here?
No, the bond.
Oh. You want, this.
Yeah, why can't?
Does anybody know why I wouldn't do that?
Oh, I know why, because that has 3 bonds and those can't.
It could, yeah, it can't have 3 bonds and a formal charge 0 is the problem. Okay, cool. Alright, so now we go to the ring. Biggest ring, always consider ethers. So you can have an oxygen in the ring. So there's a couple ways that can happen. That. Now make sure you don't draw a double bond and a ring. It's double bond or ring. So be that. All kinds of fun options. We could have this. Can't think of another one unless somebody else can. Again, this is something on the test I put down, just stream of consciousness. What can I think of within a couple minutes? Then come back to it later, because refresh your mind, take a second look at it, you might think of a couple more. And the test could tell you, like, oh, there are so many. So, yeah.
How are you able to just think of structures that has
Here?
Yeah, how are you able to?
This side.
The left side.
Left side. How did I think of these? Well, I know it has to have a double bond, right? And it has to have an oxygen.
Yeah.
So if there's an oxygen and double bond, and only one oxygen. There's a couple options. It can either be like this or like that. It's only two choices for oxygen. Okay? So if it's like this, then the chain has to have a double bond. So first I draw the longest possible chain, and so I drew that. That longest chain possible is 3. Okay? So, and that's it. If there was longer, then you could have a lot of branches and stuff. This can't really have any branches. It's too short. Hello? So now, I can't put these 2 together because this already has a double bond. So only this can go here. But if I put that, oops, without a double bond, then this can go on this one. And so I just think of where's all the possibilities this could go here. Well, 1, 2, 3. 3 carbons, 3 choices. Where's all the possibilities this could go? Here or here. Or if I put it here, it's just like putting it there. So then I just kind of draw all those out. So it's a little more intricate when there's oxygens. If there's, because the oxygen could have a double bond, or it could be an OH. Or then I also think, oh, there's the ether possibility. So I'm running through my mind where are all the possible functional groups. Oh, one oxygen could be an ether, so then it'd be something like this. However, there better be a double bond in it, because it has to have a double bond or a ring. So then either double bond's here, here, or here, but the double bond can't be attached to the ring because the double bond can't be attached to the O because the O already has 2 bonds. The only possibility was this one. This is just scratch work at the bottom. Okay? So that's what's going through my mind. And then for these here, I'm thinking the biggest ether ring, and then kind of go smaller from there. You can't have a ring smaller than 3 members. So I know I can have 4 because there's 3 carbons in an O, and then I just get smaller from there. Whether it's ether 3-membered ring or non-ether 3-membered ring. Is that okay? So I'm putting kind of functional groups together with this knowledge. Right there. Okay? Yeah.
Question?
Yeah. On this?
Yeah.
Okay.
On the test, if there's a structure that had potential for a cis and a trans, if it said draw all the isomers, would we have to draw the cis and the trans?
It depends what it said, if it says structural isomers, no.
Okay.
But if it says, you know, all structural and stereoisomers, yes.
Okay.
Yeah. I mean, lately, if you look on the test, we've been separating those out just because it's easier to grade and easier for you to organize.
Okay.
Yeah, it doesn't have to be that way though. Did you want to only, is this all you wanted from this problem, or you want to do the other parts? We didn't do the stereoisomers, which is fine, these are just the structural isomers. It's up to you.
How would it be asked on the final?
It could say, again, draw all stereoisomers and structural isomers, which we didn't do, we only did structural. Or it could say part A, draw all the structural, part B, all the geometric, part C, all the optical.
Can we do that? Like,
Okay, so then for the geometric, you'd want to find things that can have cis or trans. Rings can have cis or trans, and double bonds can have cis or trans, so anything here. So you look through, but you need something on either side of the double bond. So this won't work, that won't work, this won't work, and none of these would definitely not work. These don't work because there's nothing over on the left-hand side to cis and trans with. This is the only possibility. It's drawn as trans right now, a little star by it. So you'd have to draw, here's the trans and the cis. Something like that. Then none of these can cis and trans because you need two things coming off the ring, two different branches. So there's no geometric isomers here. You could do optical isomers. I'll do those over here. You need a carbon with 4 stereocenters. Now there may or may not be one, but you should look. So the only one that I could see, let's see, is this one right here. Has 4 different groups on it. So you could draw the cis and the trans. That. Oh, not cis and trans, sorry. R and the S. Is that okay? So we might also have you label these. So you would label this trans, this cis. Then you would label this S and R. Is that right? I think so. Is that okay? Anything else on this? Or anybody, any questions on this one? Yeah.
Okay, for stereocenters, I guess not exactly like a ring, but for like a chain. If you're trying to find 4 different groups on a stereocenter, do you count, like if it had like a chlorine and then like a methyl group and then a hydrogen and then a chain on the other end, would you count the whole chain, or would you just count the carbon that it's directly bonded to on the chain?
So you want a methyl, a chlorine, and a hydrogen like that, and a chain?
Exactly, yeah.
So what do I want to count? You mean where's the stereocenter? Is that your
No,
question?
it's that like the 4th group is like on the left. But I don't know if it's the entire chain or if it's just the carbon that is like where number 2 is. Because like all of those carbons would have a higher molar mass than just the one chlorine.
Oh, I see. When you're doing priority,
Yeah.
you only go to the first point of attachment.
So, okay.
If there's a tie, then you go to the next point of attachment.
Okay.
Still a tie, etc.
Okay.
Until you break the tie.
Okay, thank you.
Okay. All right. Anything else on this one? Okay, next. Yeah. What's the question?
Oh, it's
You don't need to name that. You only need to name alkanes, cycloalkanes, and alkyl halides. So that's a ketone. Okay? Yeah. Okay. Who's next? Yes.
So for the R and the S that you drew, are they they're opticals of each other?
They are, you could say they're enantiomers of each other, you could say they're mirror images, you could say they are optical isomers,
Okay. And do they
you
go
could say
under,
they're both chiral.
do they go under the geometric isomers?
No, if you take a look at the reader, do you have this handy? Yeah, okay. It's in the, I didn't repeat it, maybe I should have, it's in the transition metal section. I just kind of drew from past knowledge, but maybe in a future quarter I'll copy and paste it in there. Gotta go, let's see. Where's the isomer section here? It's kind of the middle of the transition metal. There's this isomer flowchart on page 48 for my spring one. Find that. So you see one category structural and another category stereoisomers. Within stereoisomers, there's two subcategories. They're geometric, which is cis and trans, and optical, which is the R inactive stuff. So optical and geometric are both types of stereoisomers. Okay? Yeah. And there's more categories too, but that's the only ones we need. All right, yes? And I'll come to you next. Yeah?
For page 103.
Page 103. This is summer 10, okay?
Please go over 18B.
18B, what's the problem? Or is just go over it in general?
I thought it was boron, but it's oxygen. No, it's the other way around. I thought it was one over the other, and I don't know why.
Okay, let me write them down then. We'll kind of take a look. Okay. Do you want to just focus on those two or look at all of them?
Those are fine.
Okay. So, it's helpful to get the protons and neutrons on both of these. Anybody, how many protons have boron?
5.
5, so that must mean the neutrons are 5. How about oxygen, protons? 8, so neutrons must be 10. Alright, it might be true that you see a magic number here. However, what's going to take priority when protons and neutrons are equal and Z is kind of generally less than 20, less than or equal to 20, that's what you'd expect. So I'm going to prefer the top one over the bottom one. Magic numbers are kind of down on the list of priority. Usually, for small nuclei, that's more of something you would look at. Is that okay? Yeah. That's how I'd choose the top one over the bottom. Yeah.
For drawing the isomers again,
Oh.
could you draw a geometric isomer for the cyclo?
This one
Yeah.
wouldn't have a geometric isomer because there's no cis and trans. You'd only have a geometric isomer if you had two little branches off of this. Then you could draw, let's draw the cis, would be this. But since there's not that second branch, there's nothing to be cis with. Meaning you need two things to be either on the same side or opposite sides. Just like here, there's two things to be on the opposite side or the same side of the double bond axis. Where here, there's two things, but you need one over here compared to one over here. Is that all right? Yeah. Okay, cool. Drake, yeah.
Yeah, it's on the practice exam on page 118.
Page 118, everybody. I can flip over there. Pretty close. Okay, what number?
17. I didn't get like the second box and the second box.
The second, the row you
Or
mean?
row, sorry, in the fourth.
And the fourth row, so we want to do both of those. Okay, this is spring 2003. All right, for the second one we've got, I'm going to redraw it. I can't really draw that way. I can, basically those two are cis right now. Two methyl groups are cis, is that okay?
Can you tell
They're-
them because that's where they specified?
They're both pointing in the same direction.
Okay.
Yeah, so That hasn't answered the chiral or achiral, but in the designation you could say cis.
Are those like the two that are drawn?
Uh-huh.
Oh, okay.
Is that okay?
Yes.
Okay. So that's the first part. We haven't done the second part, which is the chiral or achiral. Okay. And there's another answer you can put for the designation. We'll do that in a second. Okay. When there's two stereocenters, when there's more than one stereocenter, it could be helpful. I would encourage you to draw the mirror image.
Oh.
Okay. We really did this more when we were doing transition metals. We haven't done it, I don't know if I did it all in class, because we haven't really come upon this scenario, or we did, but nobody asked me a question about it, so I didn't do it. But are these two the same or different? They're the same if you just rotate 180 degrees. So, if the mirror image is the same, is it chiral? No, achiral. So that's why it's achiral. Or another way to say that, when you have two stereocenters and it's cis, it's not going to be chiral. The one we did in class was trans. I don't know if you remember, it looked kind of like this. I don't remember exactly what it looked like. Hi, welcome. More seats over here. And trans the mirror image is not the same.
Okay.
Yeah.
Thank you.
So you could also, the easy answer for the designation of this one was cis. If you want to do the hard way, you could have named R and S, whichever one it is, for top and bottom.
Okay.
So it would have been, let's see if we do this one right there. I think it R, and then this one right here would be S. RS would be an optional second answer.
Okay.
That's the harder answer, but it exists. Hi, welcome. More chairs over here. Yeah. Or floor space, whatever. Or you can sit right next to me if you want to sit here awkwardly. So that's the first box. You want to do the second? That's the fourth row now?
Yes. I was just confused because I was doing the
Yeah. No, it should follow the same procedure. Let me draw it. Okay. Then you do your order. 1, 2, 3, 4. Are you okay with the order? Okay, if you're doing the paper method for R and S, then you switch the 4 with the dash position. And then I rewrite the numbering. And then ignore the 4 and connect from 1 to 2 to 3 in arc-like fashion. This is turning left, so this must be right. Yeah.
Okay, so it doesn't matter that it's not in the wedge position, it's just...
The wedge, that doesn't matter. You just need dash to switch with 4.
Okay, awesome.
Wherever the 4 is. Okay. Yes?
On the first one we did over on
This?
yeah.
Yeah.
Is it, like, this may sound really dumb, but the, like, blackened part on the bottom of the cyclo
Yeah.
chain, does that mean anything, or is that just showing?
Yeah, that's like artistic rendering.
Okay.
So it's just showing you what side of the ring is closer to you.
Okay.
So I drew the ring flat, but that's indicating the ring is edge on. If you imagine like a frisbee
In
or a
which case
disc,
the method
it's
is-
drawing it like this for you.
So they would be like this.
The dark parts are closest to you.
Okay.
Yeah, it's a pretty typical way of drawing it.
Okay.
But obviously I can't, normal people can't draw that way, so I just redrew it flat.
Okay, thank you.
Yeah. Yes?
What would a trans version of that look like?
Trans. you just make these go in the opposite. Either pick one to be wedge and one to be dash.
Okay.
Yeah, that's it. So its mirror image would be different. So this is chiral. This one is not. Yeah?
If I was given the equation on the right, yeah, ask if it's chiral or not.
Is this chiral or not? Yeah.
No, the one on the right. So if the 4 is in the dash position, and ask if it's chiral or not, do I say yes and then, like, what do I switch it with?
This is definitely chiral because it has 4 different groups on the stereo center, which is right here. Okay? If 4 is already in the dash position, you don't need to switch it. So you just leave it where it is, you do the arc, just like we did, and it's S. So there's no redrawing of it.
But what if I want to draw the other one? Do I just like switch the one on the right and left?
Which way do you want to draw it? Oh, you want to draw this.
Yeah, I want to
You want to draw the mirror image.
Yeah.
There's 2 ways you can draw it. You can literally draw the mirror image. So can I erase this one?
Yeah.
Okay. The literal mirror image would be drawing the mirror plane. And then you just gotta make sure you got everything all mirrored. So you can do that. That's probably it takes a little more artistic mental gymnastics. The easy way to do it is you can just pick any 2 at random. So pick number 1, 2, 3, or 4. Pick 2 of those 4 numbers. Why don't you pick any 2?
1 and 3.
1 and 3. So I'm going to keep 4. This is only random. We didn't discuss this ahead of time. Totally random. Pick 1 and 3. I'm going to put the 1 up here and the 3 here. These are now mirror images. By flipping any 2, I've made it a mirror image. So actually these 2 are now identical. Okay? Yeah. So swapping any 2. Oh, it's cool. My bad. Yes?
I was just wondering, on this problem, it doesn't like specify whether or not you have to say all the things for like designation. So would you have to say like cis and then the
I think we
RNS?
accepted most and either, and I think most people just put cis because that's like the easiest way to do it. Let's see. The answer, I might list all of them. What is this? No, we just even list cis. But I know in other finals when that's happened, we list all possibilities, and then we had to accept whatever people put down.
Okay.
Yeah.
Thank you.
If I wanted more, I'd have to ask for it
Okay.
specifically. Like, we want both the cis or trans and then the R and S kind of designation. Okay. Cool. Who's next? Yes.
So on this, there were a couple of practice exams that asked to designate E versus Z, and
Yeah, you don't have to worry about that. E and Z, I think sometimes depending on the instructor, we'll put it in this kind of question, we'll add E and Z in there. Because that you could answer it that way, but just for completeness for the other instructors, but I usually haven't taught it. E and Z is a more fancy version of cis and trans. Z is cis and E is trans.
Okay.
That's it. And for more complicated molecules, that system is more helpful than cis and trans.
Okay. Awesome. Thank you.
All right. Or if we're out of questions, we can just stop. Oh, what's up? And I'll come to you next, okay? Yeah.
A quick one. So, neutrons, what, in terms of like penetration, where does that fall? Like, like least penetrating radiation?
Yeah, that's an interesting question. I'm not sure.
Okay.
Yeah.
So we just have to rank the 3 then?
Yeah, the only ones we ranked were alpha, beta, and gamma.
Okay, awesome.
Okay. Was it you? Yeah.
Yeah.
What's up?
Okay, so how do I know what nuclei goes under like what kind of radioactive emission?
Whoa, let's see this. What do you got here?
Alright, it's one as well.
What number? This one? Oh, this is the additional practice final 121. If I ask you something like this, then I have to give you, and I don't know if I even gave it on here, I have to give you the belt of stability graph. Hold on for a second. Oops.
Which problem? Which problem?
The belt of stability graph, which, wow, where is that? Which I have given on finals before, and you just find the number of protons and neutrons, and you look it up on the graph. Yeah, it's pretty easy when it's there. Let's see. Yeah, this graph right here, but it would be a fancier version of it. This is page 144. It'd be like the one that's artistic rendering, not what I did on Word. Okay. Yeah, but that graph. Is that okay? So that's how that was solved. All right, who's next? Yeah.
So on page 69, number 12, I get like the general concept of the wavelength versus delta, all that good stuff, but I'm just not sure how to rank the different ligands. If there are more like combinations of ligands.
Oh, okay. So this is summer 16, number 12, page 69. How to rank the ligands.
Yeah.
So amine should be the strongest, and I think then water and then Cl, right?
Right.
And you can get that from the spectrochemical series. You don't have to memorize that.
Right.
If we mix them, so for example, A and B, A has no Cl's and then B has one Cl, it just takes it down a notch of field strength.
Okay.
Yeah, so A would be stronger than B, as an example.
Okay.
And then E would be the strongest because it's just NH3. And then, let's see, and then C and then D, because
Okay.
you're adding CLs on. So you go by the strength of the strongest one, and then take it down notches by the weaker one.
Okay.
Is that okay?
Mhm.
Yeah.
Yeah, that makes sense. Thank
Great.
you.
Okay, who's next? Yes,
For, on page 104,
104,
for 20B,
20, part B, yeah.
could you add bromine anywhere on the carbon chain?
No, we're looking, see the instructions, this is summer 10, number 20B. See where it says draw the structure to represent the principal or major product? Gotta do the tertiary. Yeah, if it doesn't say that, I mean, we imply that in the question. We're wanting the major product, so a lot of organic reactions will have minor products, but we're looking for the major product. Is that okay? Yeah, that's it for that one. Yes?
I was wondering if you could explain the particles leaving the nucleus through the tunneling effect.
From the reader?
Yeah, it's page 134.
That just means that if there's an atom and say here's a nucleus, say something undergoes alpha decay. So it's just lost 2 protons and 2 neutrons. In order for something, so a chunk of the nucleus is just left. Okay, so that's gone. In order for that to happen, energy is required. So just like we did R goes to P, this energy or activation energy is required for such a thing to occur. And it's a pretty big energy. However, when this happens in nature, this typically does not have the energy to do so. And so it somehow just does this. Bypassing, or what we call tunneling, if you imagine this as a mountain, from here to there. So however that happens magically, we just call it tunneling, that it is paying for something, it is getting a product without paying the consequences of doing it.
Okay,
Yeah.
and that's why you say, like, remember that decay is spontaneous with energy input?
Yeah,
Okay.
yeah, so it's a spontaneous process, there's no energy input, but it still happens.
But it, like, shouldn't be, but it
It
is.
shouldn't be.
Okay,
That's right, yeah, it's all weird like that.
thank you.
But in modern science, everything has a probability, so the unlikely is still possible. Okay, what's next? Yeah,
Can you do
what page?
78?
Page 78, let me flip there first. Okay, what number?
26. I know how to do part A, but I got lost on part B because.
Okay, so this is final summer 16, number 26, page 78. Yeah, so you got lost on part B?
Just the mass for one of the products isn't given, so.
Okay, carbon 11. So I get the 6 from the periodic table. Goes to boron 11. From the periodic table, this is 5. Positron emission, which we could get just by looking at the balancing. This has to be 1 and 0. Alright. You don't have, you need the mass, you probably mean of the beta particle. That's, if it's going to be a beta, let's see what else might there be. A neutron, a proton, electron, all that kind of shenanigans. That's going to be given on the back page of the exam. So, something like where, if you look on page 4, it says mass of the electron, mass of the proton, mass of the neutron. In this case, I think that we've varied on how we've given it to you. This is given in kilograms, so you have to convert to you. Look at these numbers right here. You need that number right there. Yep. And you need to convert it to you using this. Okay. Yeah. Is that okay? Yeah, sometimes we give it to you and you on the back of the exam and then you just use it as is. Is that alright? Okay. So yeah, again, beta particle, proton, neutron, those masses likely will be on the back page. Not necessarily given in the question. Okay, 1, 2, 3. Unless there's a question on this. Okay, 1, yes.
Would you mind doing C?
Let's see. Okay, now I lost it. What page?
Sorry, 78, 26.
Okay. Alright, C, from 2A, kinetic energy is 1/2 mu squared. It says all the energy is kinetic energy, so answer from part B is right there. All the energy is converted to kinetic energy. You want velocity, so you want that number, and then it says positron, so you want the mass of the electron from the back of the exam. Is that okay? Uh-huh. That was it.
Thank you.
Okay. Was that all of your...
I was just going to ask, do we have to memorize the conversion factors, or would that be given to us on the exam for like AMU to kilogram?
No, that is all given. If you want to memorize it, that's additional fun you can have. If you do enough problems, you'll probably memorize it. Okay, did I answer all these? Okay. Yes?
What on that? So does the mass of the electron have to be in kilograms? Or
Yeah, what do you all think? What's the units of this mass? What's that?
Is it kilograms per something?
It's kilograms. Why is it kilograms? SI units, right. Joule. So this has to be in kilograms, and this has to be in meters per second. This is a SI unit. Well, if you have my 2A class, I guess you did. SI unit only formula. So when you're using joules, then this has to be in kilograms, and this has to be in meters per second. Okay. On this, or the question?
Is it on the back of the exam?
Back. What's up?
That equation?
Probably. Yeah, if you had to use it, yes. Yeah. Yes.
I was wondering if you would need to know about nuclear reactors and weapons of mass destruction.
And what was the second thing you said?
Weapons of mass destruction.
I think it's interesting. But you mean for the final probably? No.
Okay. Because I was just wondering, because I saw some problems on the summer to the system.
Yeah, I don't think Chamberlain covered it.
Okay.
Or not what I did. Absolutely.
Okay.
Okay. Yes?
I have a question on the discussion worksheet.
Okay. Yeah, bring it up. I didn't bring mine. Or pass it on. I'm landlocked over here.
Oh, it's not.
That's okay. No worries.
That electron particle.
Okay. Oh, rocking it old school, way back. What? Any particular question on this? Just what this says right here? Okay. So we've got. This is from one of the discussion worksheets somewhere. Okay. So you want to know how many moles of electrons are transferred per mole of oxidizing agent in the electrochemical. So you got to write out the reaction. Do you want, there's two ways to write out the reaction. We can do it from scratch if that's helpful to you, or you just copy it from the table given on the finals. It's up to you. Which way copy? Okay, so you go, I'll keep this for a minute here so I can remember the question. So you go to the final, the redox set of reactions. And then you say, okay, let's find silver. Somewhere around here. So you gotta go silver solid to silver 1, that reaction. Here it is. So in the table, this is listed. I don't know if it's written the right way or the wrong way yet, but I'll just write it down, and I'll write it down with the number, but I don't think we need the voltage. I'll write it down anyways. The other one, I need the one with MnO4 and Mn2+. What do I do with the carbon solid? What's that? Pay no attention. It is what? Just the electrode, yeah. So don't look for that. Okay, MnO4. Okay, found it. It's right next to the silver. MnO4. So I'm just copying this down literally from the table given on the exams. 8H+, 5 electrons, goes to Mn2+, plus 4 waters. And that voltage, though I don't think we'll need it, 1.51 volts. Okay? So that's just copy. You can balance it by hand too.
I noticed that there's like 2 different tables that you gave to us.
Okay. Could be.
Which one will you be giving to us?
When the final's kind of all nice and packaged and done, I'm planning on sending you the back page.
Okay.
Meaning the equation sheet, not like the last question. Okay? So. Alright, so now what are we up to? Got that. Okay, which one do I flip, top or bottom? And there's a couple ways you could answer the question. But, I mean, not multiple answers, but multiple ways you could figure out the answer. Top, because? Yeah, there's 2 reasons you could say that. One is, this is the oxidation side. So that's flipped. The second is, you want a positive sum. Both are true, and we'll get you to the same answer. Okay, so I'm flipping this one. I'll just put a -1 here to remember to flip it. Okay, so first I need to identify the oxidizing agent. What the heck is that?
The one that reduces.
Okay, it's the one that gets reduced, and which one is that? This one? Okay, how did you know that? Sounds good to me.
It reduces.
This one is the reduction reaction. Yeah. If I wanted the one that got oxidized, what would I pick? Which one? Silver, there's 2 choices. Which one?
Silver solid.
Silver solid, because I'm going to flip it. Remember, you're looking for a reactant. If you're looking for oxidized reduced. So the silver solid. Alright, so this is the oxidizing agent. Now, I need to balance this silly thing. So, I'm going to rewrite that one on top again. Ag goes to Ag plus, because I want a number of moles transferred. Okay, I need to multiply the top by what when I add these two?
Wait, 1.
1. And the bottom?
5.
By 5. Yeah. Okay, so how many moles of electrons are going to be transferred? It is 5 per 1 mole of this. Okay, because it wanted moles. It wanted moles of electrons transferred per mole of the oxidizing agent. So it's 5 over 1. Is that okay? Wait, now I forgot who asked. You asked.
Yeah.
There you go. Yes.
Can you go over the answer choices for?
Where?
Okay, let's see if there's any on this. But yeah.
I have a question on this.
Okay, yeah. Go ahead.
So since it was
Well.
asking about the moles of electron for the oxidizing agent,
Yeah.
if it was asking for like the other one, would it just be 1 because there's 5 moles of electrons for like
Yeah,
5?
if it wanted it per, I lost it now. Electrons transferred per mole of the reducing agent,
Yeah.
5 over 5.
Yeah, and then
Yeah.
1.
1 is the answer. You're talking about number 12. Oh, moving on. Okay. Page 69, summer 2016, number 12. What's your question on these different choices here? How to rank them?
Yeah.
Okay. So this is that color question. First you need to rank, you've got 3 ligands, NH3, water, and Cl. If you look on the spectrum chemicals here, they're ranked in this direction. Okay. When you have like a mixture, so for example, the highest rank would be E, because it has all amines on there. Here, you can hold this so you can see your own. What page was that again, 78?
69.
Perfect, okay. 69. The highest rank would be, for delta, would be E. And then you've got a little bit of mess with some CLs in there. So the CLs would just take down the highest ranking one. So the next one would be, if E is first, then C, then D, because you're adding CLs onto it, and then A, and then B. Is that okay?
So isn't strength inversely proportional to wavelength?
Right, then wavelength would be the opposite of what I just said.
But then the answer is...
Hi, welcome. There's space over here. I don't know. I didn't work through the answer yet. Let's see. You want the answer to be E.
No, it says it's E, but I'm used Y because it should be like
Yeah, it should be
the
the
smallest wavelength. It says it's common.
Okay, let's see. I gotta read the question now. Of the following, so do some erasing here. So Cr NH3 6 3 plus. Okay, of the following ions, 3 appear violet, 1 appears blue-green, 1 appears yellow. Which one is yellow? So now you need to, this would be the highest delta, lowest wavelength. Okay, now I need to go to the color wheel. We'll flip over there. So you're looking at your color wheel. Now what are the colors here? We've got violet, blue, I'll just put blue, B for blue, and yellow. Okay? Blue, green, and yellow. That'll be the lowest lambda.
So it should be violet, right?
Why do you think it's violet?
Because it's the lowest lambda, so 400. Oh wait, 400 is the highest, isn't it?
400 is the lowest wavelength. 800 would be the highest, or 700.
Okay. Then why wouldn't it be, why is it yellow then?
Well, if it appears or looks yellow, it's absorbing in the violet.
Oh. Okay.
Does that do it for you?
Yeah.
Okay, cool. So you gotta read carefully if it says absorbed or some kind of visible, just use the word appearing. Okay.
Thank you.
Yeah, no problem. Yeah.
If you were to ask to compare with another compound that has 2 ligands and one of them has one of the like weak ligand, but the other one is like strong, would that be like less strong than?
Yeah, I couldn't ask you that.
Okay.
Yeah, you'd have to kind of, you're comparing kind of likes with likes of sorts.
Okay.
Or we're changing one thing at a time. Yes?
So are you saying you can't compare C and D in both?
You do want to compare or you don't want to compare C and D? Is that
Well, I'm asking.
could we?
if you want to.
Well, I set it up, really, you know, on one end is E with the lowest, and on the other end would be B on the weakest side. Does that make sense? Because it has the water and the Cl together, so 2 of the weakest ones on there. I could have you try to like figure out each one in particular, but I kind of set it up so you can find the easiest one was the easiest to find. Does that make sense?
So
Or-
the wording is versus appears?
Is? No, absorb.
Absorb versus appear.
Yeah, absorb would be where the wavelength actually is. And like it appears, it's visible, is, all those are like what you notice by eye.
So better wording for the question would be which absorbs yellow instead of which is yellow?
If we wanted to do it the other way, the other kind of question, the way you were thinking of it, I would say absorb. Okay. I'm not sure if everybody's okay with it. Yeah.
So how would you compare C and D?
Yeah, I probably wouldn't ask you that. Yeah, that's why I asked you the E one. C and D though, C would have a higher delta than D because it has more CLs on it. So I could, I guess. I just wanted to give you like, you know, an easier one of the set. Is that alright? Okay. Ready for our next question? Or next problem? Okay. 1, 2, I saw my first. 1, 2. Yes? Jenna.
Can we do, on page 103 of the practice exam, it's like the last box on the page, it's the 1,2-dimethylcyclopropane.
103. Do that whole row of chiral and all that stuff?
Just for the last box though.
Number of hydrogens.
Oh no, I meant the dimethylcyclopropane.
Oh, okay. All right, 1,2-dimethylcyclopropane. That's that. Let's see. You want to know if it's, let's see. Identify each as chiral or achiral. Designate all that. Count the number of hydrogens. Okay. So it depends what it is. I probably have multiple answers here. Let's see. For 19. Yeah, you can see there's a lot of answers.
So can you
And oh, there's a hint. You'll have more than one answer. Okay.
but do you have to put both, or could you just, like I drew it cis. Is that okay? Do you have to draw it both ways, or could you just
Yeah, so you can draw the cis, and you just next have to draw the trans, because they told you there's 2 answers.
So you have to include both.
Yeah, you don't have to draw them, but you have to have a word answer for both.
Okay.
So you would say cis, you say trans, and now let's read the question. Designate the molecule cis, trans, RS. Okay, yeah, so let's do the RNS stuff as well. So, we did something like this just a little bit ago with the cyclopentane. Do you remember top or bottom, which one's going to be chiral? Do I remember? Bottom, yeah, the trans is going to be chiral. You can draw the mirror image. Do you want me to draw the mirror image?
Okay.
Okay, so just like the other one, the cis, its mirror image will be the same. And this one, the mirror image will be different. So we've got the achiral and the chiral here. And then you can name the R and S. That's where all the R and S stuff, do you see in the answer there? You want me to do that too?
Where would the stereocenter be?
There's 4. Here, here, well 2 here, and there's 2 here.
So I guess I'm just confused how it's attached to 4 different groups.
Okay. Let's pick here for example.
Okay.
Okay? This has a hydrogen we didn't draw, a methyl, the side of the ring with no methyl branch, and the side of the ring with a methyl branch.
Okay. Okay. Thank you.
Oh, so you're good?
Oh yeah, I think.
Okay,
Thank
cool.
you.
Who's number 2? Yes.
Page 105.
Page 105. Okay, what number?
For 23.
23, okay.
How would you solve for y?
For y. This is summer 2010. Okay, so hopefully everybody's looking at the table. That's a lot to write down. You've got the rate law. R equals A, B. I've got a K in there. You've got this one? You have this already?
Yeah.
What is it?
I think it was 1.
Okay. And you don't have this, we call it Y. So we know X, or the exponent, oh I see, of the first, the A, but we don't know the exponent of B. And do we know K? I don't think so. Alright, so on this one, you probably set, to get A, you set trial 1 and 2 equal to each other. However, for a lot of fun, for us, we didn't hold A constant for any of them. Okay, that's fun. So let's try. Let's see. Let's write this for trial 1. 3.24 times 10 to the minus 8 equals K 0.000345, that's the first power, times 0.000765, and this is to the Y power, and yeah.
Wait,
Oh.
sorry. X is 0 for.
X is 0.
Yeah.
Okay, so that's even easier. That's 1. Anything to the 0 power is 1. Okay, so now we have K 0.00765 to the Y. Okay, equals that number. Alright, so that's for trial 1. Let's see what else we could do that for. Let's write this for trial 3 now, because trial 2 uses the same concentration as trial 1. Okay? So for 3, we got 3.24 times 10 to the minus 7 equals K 0.00, I missed the 0 here, 0.00765 to the Y. Okay? Let's divide this and this. Okay. What were these two divided by each other? Anybody?
10.
Or 1 over 10?
I'm not sure. It's either 10 or 1 over.
Okay. Let's say 1 over 10. Okay, good. K divided by K, it's gone. And then this divided by this, 1 over 10 to the Y. Is that alright? Okay. So it's just 1. Yeah, so we didn't keep the other one constant, but we had an easy setup for solving for Y since the other one was 0. Cool, who's next? Oh, okay.
On page 116, number 3.
116. Okay, spring 2003. You said number 3?
Yeah.
Okay.
I just wasn't sure how you could determine the shape from the given information.
All right. You have to draw the CFT out.
Okay.
Anytime it has to do with shape, you should be drawing the CFT. So, octahedral, tetrahedral, are there any other shapes we need? Square planar. Oh wow, I think I have to redrive this one. I don't remember it. So if you're on the test, you don't know it, you gotta redrive it. Or if you want to tell me, it's up to you.
It's up to you.
No, I mean, I'm not taking the final, so I don't care.
Will you derive it, I guess?
What's that?
Will you derive it?
Okay, so you go, oh, square planar. Looks like this. Do you remember this stuff? Okay. So then you need to think of the d orbitals. If you have these in your head, you wouldn't have to redraw it. But let's say you got x and y, the y, z, the x, z, the dx squared minus y squared, and the z, dz squared, I mean. Okay? So then you say, okay, I usually start like, what's the highest and what's the lowest? So which one's going to give the highest energy?
The x squared y squared?
Yeah.
X squared y squared.
So you know dx squared minus y squared. Okay? Which would probably be next?
Let's say the xy one.
Yeah, we've got this has a component and this. And then these two have to be tied because they only have half. Okay, it's the one that looks like the Eiffel Tower. Is that okay? All right, so now go back to the problem. So that's how I would rederive it if I forgot on the test. What's another option if instead of doing what I just did? So you know you have to know the 4 shapes. What's another option besides redriving it? I would, if I was concerned about redriving it because of my mind would be garbled after, I get to this after an hour and 50 minutes, then I would just, in the first 5 minutes, this would be one of the things I draw on the back of the test, on the periodic table. So draw all 4 really quick, doesn't take long. And then when I get to a question like this, if I do, I just look there. So that would be another option for you, just so you don't have to recall so much information. Anything I think I could possibly forget, like me, I was like, oh, don't quite remember, but I know I could redrive it. But on a test, you're a little jumbled. Okay, so it was D6, and it's paramagnetic. Okay, so 1, 2, 3, 4. Let's do the strong field first. 4, 5, 6. 1, 2. Because if you did the weak field, well, let's do.
That's where I was confused.
Okay, let's do the strong field, and then we'll talk about the weak field in a second. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It's tetrahedral. It's the only paramagnetic one.
Okay.
Why did I do the strong field and not the weak field one? So strong field, remember if you forgot, you fill the bottom first before you go to the next row. So I filled this with 4, it maxed out, then I go up. Weak field, I fill everything, and then I start again at the bottom. Okay, why did I do strong field? Does anybody know? And not the weak field?
What they?
Large change.
Oh,
Large change. And then if there's ever, anytime there's a large change, you're going to automatically assume that it's diamagnetic.
Yeah, so the strong field is more likely diamagnetic. If I did the weak field, all of them would be paramagnetic, and that's not going to help me at all.
That's what I did
So I know,
first.
yeah, you get no answer, so then you should try the other field.
Yeah. Okay.
Yeah. And see, the key word is the last word in the question, likely. So that means we're not telling you, but if you drew all possibilities, it has to be diamagnetic. So really we're asking which diamagnetic one. Okay? So you can always consider both, but in the back of, even just filling it out, you can see the the strong fields tend to be diamagnetic. If you did the other way, 1, 2, 3, 4, 5, 6, this would be para. 1, 2, 3, 4, 5, 6, that'd be para. 1, 2, 3, 4, 5, 6, that'd be para. It gets you nowhere. And then, which is true, weak field tends to be paramagnetic.
Okay.
Any other questions on this one? Okay, yeah.
Can we go over number 11 on the same exam?
Same exam, spring 2003. Okay, California, no, Curium, I think. 247. Okay, let's see. And what part confused you about this one?
So, isn't it something like if the mass is less than the isomer, then it's going to be electron captured instead of anything else?
What number was it again? 12?
Number 11.
11. Okay.
Like, how do I differentiate when to use beta or, because I know there's beta the positron and then there's the negative, and then they flip it on either
There's
side.
kind of two ways you could answer this. One way, if you're not given any other information, pretty heavy nuclei will undergo alpha decay. Because the bigger can lose bigger particles, the alpha is the biggest particle. Smaller, it's harder to lose a large particle. The other way you could do it, if you have the built-in stability, you just plot it, and you'll see it's in the alpha region. Is that okay? Yeah. So that was it for that. It has to do with the size. It has to be fairly large. Like getting towards the end of the periodic table, which, let's see, it was number 96. Yeah.
So when we're
It's pretty
looking,
much at the end.
when we're looking at that, are we looking at the mass or are we looking at the isomer, like 247, or do we look at the mass of it?
It's a little easier to look at the mass, the Z, the atomic number. But yeah, I would look at Z, because that's usually what you're plotting on the belt of stability. You plot Z versus the number of neutrons. All right, next. Yes? Okay, this is another discussion worksheet. The bottom one here?
Yeah.
Okay. Okay, binding energy of silver 107. Ag 107, and I have the number here, 106.879289 U. Okay? So you want to balance this. It's the first thing I would do. So you find silver. Silver is number 47. You know it's made from protons and neutrons. There's two ways to balance it, but probably the easiest way is there's 47 protons, and then 107 minus 47, that'd be 60. And you can see if it adds up. 47 times 1 plus 60 times 0 is 47. 47 plus 60 is 107. Okay? So then find the change in mass, the mass defect. That's 106.879289 U minus 47. And now you need to look up the numbers. I guess there's a lot of digits, so I guess I should copy it down. Oh my gosh. Okay. So the proton, unfortunately, this is given in kilograms. 6726 times 10 to the minus 27 kilograms plus 60 times, where's the neutron? Let's see, 1.6749 times 10 to the minus 27 kilograms. So you need to convert both of these to U. Because this is U, that's kilograms. So both of this and that need to be converted from kilograms, and the conversion is also given right here. You basically divide by the kilograms, 1.6605 times 10 to minus 27 kilograms is a U. So you do that for both of them. Okay, you get the change in mass, then you say the change in mass, that should be a negative number. And 1 U is 1.4924 times 10 to the minus 10 joules. That would be the joules per nuclei, and you wanted per nucleon. So one more step. You're going to divide by, anybody? Divide by what number? 107. Is that right?
Yeah.
Okay. It's the same process for every single one. Really, you just need this number. Another one. This had additional conversion compared to one of the ones we did in class because I didn't have it. In class, you give the U of both of them. A new question or on this? Okay. Thank you.
AMU is the same thing as U?
AMU and U are the same thing. Yes?
Can you review how to do like MEV, the conversion to MEV?
MEV is just literally conversion given on the test. And it's on page 4 if you have the practice exam. So you just convert. So you take this thing here and an MEV for every 1.6 times 10 to the minus 13 joules.
Me too. Okay.
So it's just a conversion.
Okay.
It's another energy unit.
Okay.
Okay.
Thank you.
Anything else on this one? Yes?
Could we go directly from nuclei to MEV, or would we have to convert it to nucleon and then go to MEV?
That's true, you could do that. If it didn't ask for joules, this is unlike the one I did in class. There's a conversion from U to MEV, which could be right here. If you wanted to go straight from here to MEV, you could.
Could we just do that?
Yeah, you just look up the conversion from U to MEV on the test.
Okay.
Is that all right? Yeah.
Question on this. One of these questions, it was basically find a nuclear binding energy density like joules per atom. Is that the same as joules
Nuclei.
per
Yeah.
nuclei?
Joules per atom, joules per nuclei. Atom, nucleus is in the atom, so they both represent the same thing.
Okay.
Yeah. Yes? You would use Avogadro's number if you're going to moles, just like in Chem 2A when you're going to moles for something. So if I get rid of this, I'll get rid of this. This, one more time, is joules per nuclei here. You could be asked for joules per mole. And in that case, oops, got backwards. You write Avogadro's number, 6.022 times 10 to the 23 nuclei per mole. So now this changes it to mole. If, for example, you had 7 moles, you'd now multiply by 7. If you wanted per gram, then you multiply by the molar mass, which is this number right here. And now you have it per gram, and if there was 7 grams, now you multiply this number by 7. Is that all right? Yeah. Next. Yeah.
Number 7.
Is this, oh.
It's an alternate for that.
Oh, nice. That's cool. Number 7. It's a reaction. Okay. This is a bonus secret question, which you all cannot have. I have it right here. Okay. We've got reaction 2A. Goes to the products. So consider reaction represented by this. The reaction is first order. Its activation energy is 34.2 kilojoules per mole. At 25 degrees C, the half-life is 38 minutes. We want to know the half-life at 80 degrees C. Here you go. Anybody recognize this? It is not the integrated rate law. Yeah, the one that's kind of Clausius-Clapeyron. So this would be, if you have one of these, page 4 at the bottom. It has a natural log with K's in it. This is what I'm about to copy down right there. Okay? So when you have, okay, the big hint is 2 different states. And I think this is the only time the whole quarter we learn 2 different states. Now normally, though, if you're thinking this one, you're thinking 2 different temperatures. Let me write it down. Normally when you're thinking of this, 1 over 2. You're thinking 2 different temperatures and 2 different Ks. However, this is a little weird. It's got 2 different temperatures and 2 different Ts. But you need to remember, because it's first order, half-life is the natural log of 2 over K. So K and half-life are the same thing. They're just interconvertible, essentially. So you really do have, if you call this state 1 and this state 2, then you're looking for this, which can be converted to half-life. This equals the natural log of 2 over half-life. You have this one. It's just natural log of 2 over 38. You have the activation energy. Well, what do I need to do with that activation energy? It's got to be in joules. 34,200 joules per mole. Why in joules? Because R is in joules. So R is 8.3145 joules per mole Kelvin.
Could you
And
have converted R instead of?
Yeah, if you're into that, you can convert R
Okay.
to kilojoules, whatever you find more exciting. Okay? So T2 is the 80. Well, that's perfect. 273. And T1 was the 25 plus 273. Is that all right?
Yeah.
Okay. So I would recommend you practice on your calculator and algebraically doing this. Did you get the answer from your TA?
Did you send it out later?
Okay, so make sure whatever your TA sends out is the same answer you get when you calculate, because this is a Just same in 2B. Common one to mess up the algebra. Okay. Cool. Yes.
Can you give an example of how we might apply the belt of stability?
Yeah, the belt. Somebody asked, I can't remember what it was now, but this is protons versus neutrons. And it goes kind of like that. It's a line for the first part of it, and then it goes upwards. If I gave you a nuclei, I don't know, uranium-235, then you would find the protons and neutrons, plot it, and it could tell you what kind of decay it is. Because we got, like, for example, alpha. So if it lands up here in this general region, it would be alpha decay. If it's down here, it's like beta decay. That's it. Is that okay?
Yeah.
So it's just plotting based on the number of protons and neutrons you got. Okay, who's next? Yes?
I had a question on summer 2010.
Summer 2010.
Number 14.
13.
14? Yeah.
What page? 94, okay, there we go.
It's 102.
Huh?
102.
102? Wait, but this is summer 2010. Okay, whatever. 102. Oh, final summer 2010. That's on page 102. What number?
14.
14. Stonehenge? Okay. Half-life of carbon is 5730 years. We want, the bones are 3000 from 3000 BC. Okay. So we know it's first order, so let's do the first order. And they want the fraction or the ratio. Let's see what word it used. The percent. So that's just this. Okay, lambda is the natural log of 2 over 5730. T is? Anybody?
5,010. So 5,010?
Yeah. How do you know that?
Well, it said 3,000, but then it's from summer 2010.
Yeah. So you add 3,000 plus 2010. Okay. We would have also accepted just 5,000, I think, that year. So if you didn't put 2010, some people didn't know what the year was. So 2,000. Yeah. Okay. Who's next? This is your 15-minute warning. Or we could stop. I don't know. Fiercely looking before I exit the building. Yes.
Page 113, question 28.
113, 28. Both parts, or one part in particular?
I'm just confused about SN1 and SN2 and how I'm supposed to find
You only learned SN2, so you don't need to worry about that. You don't need to worry about SN1. Let's see. And yeah, B's kind of really A. A would be kind of the one I could really ask you. So you want me to do A? Okay, we've got C, H, 3, C, C plus, again, it's fall 2006, number, page 113, 28A. Okay, well, I was super nice in the question and told you it was a substitution. So you know it's the SN2 reaction. Where's the leaving group? Which one? Br. It's the one on the organic molecule. Okay, what do we call this? The nucleophile. It's the one that's going to substitute with, or easy way, you're looking for something with electrons or a negative on it. So then this is going to substitute for the leaving group. So it depends which way, what you want to write first. But if you write this one first, then it would be that. Or you could write it the other way if you prefer. You just have to invert that. So this was the original part, this. And then the nucleophile is this part. It depends. It doesn't matter which way you write it. Is that okay? Yeah. So the negative thing swaps for the leaving group. Leaving groups are commonly halogens. Okay, so it's just a substitution. One substitutes for the other. All right. Somebody else had their hand up? Yeah. Oh, you found it.
Yeah.
What page?
Number 87.
Page 87.
Number 11.
Number 11. This is summer 2015, number 11. Okay. Can I erase this? Okay, you need 5 milligrams of barium, 128. The half-life, which we'll know is first order, is 2.43 days. How many milligrams of BaCl2 let's see. So the researcher needs to order, how much must she order from the manufacturer if shipping takes 4.5 days. And they give you the molar mass of this, it's 128 grams per mole. Okay, so she orders it from the manufacturer. She wants to know how much to order because it's going to take 4.5 days to get to the university. And by the time it gets to the university, she wants 5 milligrams of the barium. Forgot who asked now. You asked, right? Does that make sense? So it's going to decay, so you want to order more than 5 when you start off with. Okay. So the first order integrated rate law. Is this lambda is going to be the natural log of 2 over 2.43 days. What's the time going to be? 4.5, yeah. Okay, so we got both of those, so we can get this ratio. That's good. So I know well, let's do a little calculation. So we've got 128 Why was the molar mass given? Let me make sure I have the right molar mass. Oh, the molar mass, this is just the barium. Why was the molar mass given?
It's the radioactive isotope.
Yes, but, and what will I do with the molar mass? Because I need it given because I might not be able to look it up.
You have to convert it.
What's that? I need to,
So,
yeah, because I need 5 milligram of this only, but I ordered this. So I need to do a little Chem2A calculation right now. So maybe I'll start like this. 5 milligrams of 128 barium. So that's what I want. Let's find out how much barium chloride that is. Okay, what's the first thing I do? If I want to find out how many milligrams of barium chloride it is. Okay, sure, let's convert to grams. Now what?
Reduce the molar mass given.
Sure, molar mass. Now what?
Ratio, which is 1.
Okay, there's 1 of barium for every barium chloride. Now what? Yeah, so you need to find the molar mass of barium chloride, which would be 128 plus 2 times that of chlorine, 35.45 grams per mole. So this would be the mass of barium chloride to order, or that's needed upon arrival at the university. Is that okay? This is the mass of barium chloride needing to arrive at the researcher's lab after 4.5 days. Because she wanted 5, right? But it comes in the form of barium chloride. So this is my Chem2A calculation to get to the mass of the barium chloride as a compound. Okay. Where does this number go in my calculation?
N.
Okay, why N?
Because that's what you need after the time has passed.
Yeah, so solve for N naught. You got N, you got lambda, you got T. Is that hurting? So this was the, if you're fuzzy on 2A, this would have been the hardest part, I suppose. Okay? Okay. Next, 5-minute warning. Yes?
Can I do this one? Number 15.
Summer 2016, page 75. I think this will be our last question before the review session starts. Sigma, pi, h, and sp3, all 4 of those parts?
No, number 50.
Oh shoot, I have to do all that stuff? Okay. Okay, forget it. Erase this from your memory banks. Okay, page 75, final, summer 16. Which one? Oh, I forgot. This one, 15. Okay. The half-life of uranium-238 is 4.51 times 10 to the 9 years. This decomposes into lead. So through radioactivity. A rock contains equal masses of both of these. How old is the rock? Okay. So again, first order integrated rate law. Equals e to the minus lambda t. Lambda is equal to the natural log of 2 over the half-life. Is that part all right? We want t. So then we got to figure out this mess. Okay, we know we have an equal amount of both of those. So let's just for fun pick a number. Let's say there was 100 atom or nuclei of the uranium to start off with. This is original. Okay? After how much ever time that passed, we don't know how much time, now it's equal amount of each. So that means there's 50 of the uranium and there's 50 of the lead. Is that okay? There's half of each? Okay, so what number is this, what's this equal to? Yeah,